So that's then the last step, the fifth step, the program expansion of functional in fluctuations around the mean field. So this is deriving the effective theory. Which is the last step 5 in the program. Okay. So this would be derived S of phi as mean field plus fluctuations, and then derive an effective theory in the fluctuations. Okay. So here, just let's recall. We had found the trivial solution for the mean field equation, so let's denote for simplicity the fluctuations not by delta phi but by phi. Okay, this is just for notational simplicity. Okay, so the phi from now on will just describe the fluctuations. So then the basic idea now, which again is all like where physics enters and where like the purely exact mathematical formulations do not hold anymore, well, you assume that this expansion in the fluctuations is well justified. So assume that you have small fluctuations which allow you an expansion of the effective action in terms of small phi. Okay, and this is again just an assumption that you do, and you have to see if this is indeed justified and leads to reasonable results. And this now really only works well if you did everything right and made the expansion around the right mean field. If you in a way have some, let's say you have some mean field which breaks some symmetry, this is the right mean field and you want to make an expansion around this can be fine. But if you chose the wrong mean field, let's say you're up here, and you try to make an expansion, you will see that your quadratic fluctuations will just be unstable. Okay, so you made the wrong choice of the mean field solution. Okay? So in our case, however, everything is like, or in our case, everything is simplified due to the trivial mean field. So what we start out from, so the phi now denotes fluctuations, and well, the mean field itself is trivial, so we will only have the theory n1 phi. Minus trace log times my omega plus t squared. Okay, so we have this theory here. Okay, so this here is already quadratic, so that's everything fine. So now we want to make an expansion in this phi here. So this is small. Okay, so let's just consider what is written here. So this is the Green's function, the inverse of the Green's function of the electrons in the fluctuating field phi. This here is just the inverse of the Green's function of the free electrons, okay, where there's no coupling to an electromagnetic field. So let's give this a name, because this is important. So let's call this the free Green's function of the electron gas G0. That's like the one we used also in our perturbation theory. So then the expansion can be done by reorganizing this term. Okay, so let's do some simple mathematical manipulations which then allow us to organize an expansion of this trace log in small phi. Okay, so let's just here use the following. So trace log G0 to the minus 1 plus L cubed of phi. Okay, this we want to somehow, this is organized quadratic in phi, this now we want to expand in phi. So how can we organize this? We can use, again, due to the trace log here, to base all like normal manipulations that we know from functions, okay? So we can use here that we can write this as j trace log g to the minus 1, then we have a 1 plus g0, so I just pulled out the factor here, and then we have here 5. Maybe I should give them heads to recall, well, here we're talking here about these operators, these large matrices, okay? So I just made a simple like manipulation. Well, here nothing so far, it just pulled out the g0, okay? And now we can use the property of the log known for numbers, ln a times b is ln a plus ln b, and because of the trace, it also holds for operators, okay? So we can write this here as trace ln g0 to the minus 1 plus trace ln 1 plus e i.e. lq oops, g0 times phi. Okay? So what did we gain from this? Well, now we pulled out here the means function of the non-interacting electron gas. Okay, so this is just the determinant of this operator, which is just the partition function of the non-interacting electron gas. So this would be z0. And this is now only the part that depends on the fluctuations, and we have here 1 plus this operator where we think that this phi is small. So this now we can nicely expand in the logarithm. Okay, so we can use here the expansion of the logarithm. So we can write this as g0 to the minus 1, then we have a plus LQ trace g0 phi, and this trace again contains the sum over spin and the sum over internal degrees of freedom. Okay, so if you want to put out spin, you can already write the factor of 2 due to spin. And then the next order, which is from the expansion a minus, but then I squared gives another minus, so there's a 1/2, and the spin gives a factor of 2, so e q square trace g0 phi g0 phi plus and so on. So you can systematically expand. Okay, let's write this better. Like there would be a 1/2 due to expansion of the log, and there's again a factor 1/2 due to spin. Okay, factor 2 due to spin. And then you can easily go to higher order. Okay, so there's now a systematic way how we can derive an effective action in the phis. Okay? So, let's see. Again, this here is the matrix product, okay, of the operators, and this would be the free element. So now we can simplify this first. Okay, this we identify what it is. What about the linear term? So the linear term, well, we are expanding here around the mean field solution. So the linear term is just 0, no? There are no linear terms if you expand around the mean field. Since we have an expansion around the mean field. Mean field solution, no? Mean field means here solution of the mean field equation. Okay, so we arrive with this term and then a quadratic term. Okay? So the effective action is then given by this times this, but now we can actually recognize what this here means. Trace g0 phi, g0 phi. So if we look at this again diagrammatically, we have a g0, we have a phi, we have a g0, we have a phi. Okay? So if you translate this, you can write this now down in real space, and this would be g0 of x, x prime, phi of x prime, g0 of x prime x, phi of x, and you would integrate over x or x prime. Or if you make the Fourier transform of this, this would be g0 of p. This is now diagonal because it has only it doesn't have the potential anymore. G0 of p, phi of q, G0 of P plus Q, phi of minus Q. Okay, so this would be just this kind of diagram if you do the Fourier transform. So it's always, I mean, you can do it formally. So just like to get used to it, like I always first had to write it down in real space because it's like the easiest. Okay, because this operator is somehow stupid because it has this, you don't really know how, like you have to get used to it. So if you don't know what is going on, the best thing is first write it down in real space. So it's a convolution, x prime, x prime, x, and then you can do the Fourier transform and you can see what happens. If you have done this like 5 or 10 times, you will recognize what it is and you can just immediately always identify these diagrams. So if you are confident and already see what's happening, you can just already think in diagrams like it's always momentum conservation, 3 means line. But then we see, well, what is this? This is a product of the Green's function Gp plus Q, Gp, and we have here a sum over P. This here is just the polarization operator, no? So if you look at this here in real space, this is the sum over P, momentum space G0P, G0P plus Q, phi of Q, phi of minus Q. So this we can write as the sum over Q, the polarization operator at Q, phi of minus Q. Okay? So notice trace G0 phi, G0 phi. If you change this momentum space, well, there's some factors due to the Fourier transform. Then we have here the four momentum P and Q, G0 P plus Q, phi of Q, G0 P, phi of minus Q, and this is nothing but this is nothing but so let's put here, okay, 1/2 Q, phi of Q, phi of this is nothing but polarization operator which we define with the factor here, so this is why we 1/2. Okay? So if we do this expansion up to quadratic order, so if we do this expansion up to quadratic order, we will have this term, we will have this here, which is phi of Q, phi of minus Q is the polarization operator, and we will have this here. Okay? So we can write down effective action for the phi field. So if we write down all the prefactors in the right way. So I said you always have to be also careful that in momentum space this would be just the trace of x and x prime, but if you go to the momentum space there are some factors due to the Fourier transform, okay? And so you can always think, well, it has to be dimensionless, and this Green's function here carries everything. Okay, so if you do everything carefully, then you should find the following for so this is a Q squared over 4 pi, which is probably this one here, and then we have minus E squared polarization operator Q, phi of minus Q, which is coming from this expression here, okay? And then there is, if you go to higher orders, you will find again that the third order just vanishes due to symmetry. And then the next order will be phi 4, that one is neglected here. Okay? And then there was still this trace log G0 that we don't have to carry so much about because we just put in the end right normalization factor. Okay, this just gives a Z0 partition function of the non-integrating electron, some normalization constant, but we can just just write in the end the right thing with the right normalization constant, because we know that if we put E squared to 0, this is the non-impacting electrons, we should end up with a partition function of the non-impacting electrons. So we're here, this we call polarization operator. We have been counting before, 2t or okay, so actually I'm just thinking now with the prefactors, okay, I should have been here more careful. Okay, maybe you can just see yourself if this really was the right thing with this temperature. Let's see. So probably this temperature here does not appear. So this one, okay, I can also, I didn't do one you can just see like from the Fourier transform convention. So let's see. Yeah, probably it doesn't appear because you will have like a factor t and L cubed from the Fourier transform, but then you get a delta function which sets you with, like this would be q and q prime, which sets it to the same due to momentum conservation, and this will absorb it. Okay? So you can just check this, it should come out in this way, the right form, and we know that this should be the case because now if you look at this, well, this is the propagator for the photons, the q squared, but which now got like some self-energy due to the interaction with the electrons, due to the interaction with the dielectric medium, which is polarized. This now has a self-energy, which we showed that in the limit omega to 0, the static limit, this just gives a mass to the photons, okay? Which is then the interaction, describing the interaction in the RPA approximation, which takes into account that the Fermi C is screening the photons, the interaction. Okay, so what we arrived at here now is trading the electrons. We have traded the electrons for a dressed photon field. That's what we have achieved. And dressed here means that they have the self-energy entering the propagator, which takes into account the electron, the interaction with the electrons. So this is the effective RPA potential that we identified, no? Okay. So we have an effective theory which, without coupling to electron gas, which amounts to setting the charge equals to 0, because this provides the coupling of the electron gas. Of the photons of the electron gas, we have the bare propagator, which is long range 1/r propagator, so momentum space proportional to q to the minus 2. Long range will be vacuum. This would be just this part without this one, and the coupling to the dielectric, meaning polarizable medium. The dielectric medium. This is the electron gas. In the high density leads to the appearance of self-energy, which is here given by the polarization operator P of Q. And this, we saw, will make the interactions short range and physically the simple Monson screening, which converts long range correlations into short range, and physically, and we understood that this is just a screening of charges, which is a polarizability of the electron gas. Okay? So now, if you like, we can again look at the partition function and then the free energy of the problem. So if we stick to the Gaussian level, so we just did considered Gaussian fluctuations around the trivial mean field equals 0. So we now in Gaussian integral over these fluctuations, we get the determinant of this operator. Okay, so this gives us the RPA partition function, where now the Z0 we include, which came from the zeroth order in the expansion of the trace log, and we can just here include by noting that when we set the electron charge to 0, we know that the normalization has to be such that we get the free electron gas Z0. Okay, so that's why we didn't have to take this constant factor here into account, because we can always add the normalization factor, because we know how this looks like. Okay, but this is then, if we look at the free energy, that's log, and remember that we called the free energy the one where we subtracted the zeroth component. Okay, so that's, if you recall, the free energy, what we subtracted was just the free energy, the free energy of the non-interacting electron gas. So Z divided by Z0 just kills this factor, and then we have for minus here, and we have T half log 1 minus 4P E squared Q squared. Okay, so this is just the free energy as before. Okay, so what we just did is here, we reproduced our results that we had before from diagrammatic perturbation theory in terms of the effective theory. Okay, so this shouldn't, be too much of surprising. But now we have achieved, in fact, more. Okay, up to here, is it? Okay, just a matter of calculation. But what we have we have achieved more. First of all, we have an understanding why our diagrammatic approach around taking the non-detecting electron gas as a reference point was fine, because we confirmed that the trivial solution is a solution to the mean field equation. Okay, so next we will discuss an example that doesn't have to be the case. So this is one conceptual part, but an important part is now we have arrived in a systematic way how to derive an effective theory. So if we stick to the Gaussian approximation to quadratic fluctuations, we just reproduced RPA. But now we have a systematic way how to improve the RPA expansion. Okay? So RPA approximation just amounts to like a free propagator for the photons. Now if we do here, we have a controlled way how to include higher orders. Okay? So the third order vanishes by symmetry. So the next term will be a fourth order. So the fourth order we can again think of some, now this representing here the bosonic field phi, and there's some interaction between then the bosonic field. Okay, so going to higher orders, we will add here interaction terms. Okay, so instead of having then a quadratic theory in the RPA approximation, if we go beyond the RPA approximation, we will find interaction terms which can be incorporated, like again, if you want qualitatively, and which are then beyond the RPA approximation. Okay, so at some point I think Eric was asking, like, oh, how do you organize, like diagrammatically? Like we said, like in every order, diagrammatic theory we kept like the leading order term, but then going to higher order in perturbation theory, there would be terms that are comparable with the next leading order in the previous, or I don't know, somehow of you asked that, no? I mean, so somehow how do you organize interaction term? We said, well, the way how to do this is in every order interaction just keep the leading order term. This led to RPA. So now the terms that were not taken into account, like the higher orders in every order, are now incorporated here in the interaction, can be systematically included. Okay? So for example, here we found +1 mode in the high frequency limit, which was a divergency. So there will be added some self-energy again to this term due to like correction, like if you take into account relatively now the interaction between those +1 modes. Okay? So this is like the big advantage of the theory. First of all, we did some approximation in the diagrammatic perturbations that we only now confirmed, but then we have really a systematic way how to go beyond and include higher order terms. Okay, then of course, just one more statement is that, well, what we have here then is also, if you include higher orders, is what we wanted. We have a description which is much simpler. No, we don't have to care about the electron fields anymore, because this was like the idea exchange microscopic degree of freedom by some effective field, which then allows for a much simpler representation. So the RPA just becomes a simple Gaussian theory. Because you have a simple description, we can then also go beyond this description. Okay, but then again, everything builds on choosing the right channel, and then next lecture we'll discuss another example, how to derive an effective theory where one has a non-trivial field.